And I also need to apologize to certain attendees. And this entire hotel is under central air conditioning. So it is essentially not possible to adjust the temperature. So like if you came with the expectation that Taiwan is a very hot area, we apologize, but put on an extra shirt or something. Yeah.
Good morning, everybody. Welcome to the first session of Asiacrypt. And this session will feature all the award papers. So I'm very happy to invite you all to the paper that won the Best Paper Award at this Asiacrypt, Full Quantum Equivalence of Group Action, Discrete Log and CDH and more. This is a paper by Hart Montgomery and Mark Zandri, and Hart will give the talk.
Thanks a lot, Shweta. Hi, everybody. I'm Hart, and today I'm going to be talking about the full quantum equivalence of group action, discrete log, and CDH, as well as some other related results. And this is a joint work with the always excellent Mark Zandri. So let's get started. So for a brief outline of what I'll go over today, I'm going to start by discussing some background on group actions. I'm going to argue why we should study group actions. I'm going to go over our results, and then I'll go over an overview of some of the techniques behind our main result, which is the quantum equivalence of group action, CDH, and discrete log. And then I'll go over some open problems in future work. So let's get started. You all are probably familiar with group actions. Who's used to group actions here? Some people? Awesome. So it's really a pretty ancient mathematical primitive. A group action is just a tuple of a group, a set, and a mapping that satisfies the identity and the composability properties. And you can think of the composability property as sort of an analog of associativity in groups. In this talk, I'll mostly be focused on what's called regular group actions. And these are sort of simpler to think about. And what a regular group action is, it's a group action where for any two set elements, x1 and x2, there's a unique group element such that x2 is equal to g star x1, where star is, of course, the mapping. And this leads to a number of nice facts about the group action. For instance, the set and the group have to have the same number of elements. And for a fixed set element, little x, g star x is a bijection on x. Most group actions used in cryptography are regular, and we'll warn you when we use non-regular group actions. So what about cryptographic group actions? These have a long history in cryptography, going back to the work of Kouvenis in 2006. And before we start by defining hardness, let's think about some efficiency things that math people don't really bother when they define group actions. So we're going to start by assuming what's called an effective group action. And I don't really want to dig into this definition because it's a little bit tedious, but what it basically means is that the group action works like you want it to work. Group action operations and group operations are efficient. There are efficient ways to sample uniformly random group elements, and set elements have unique representation. We'll also assume abelian group actions because, well, our results only work for those, and non-abelian group actions are not very useful for cryptography, particularly public key cryptography. And finally, since every abelian group can be mapped to the additive group of integers for some integer p using a quantum computer, we'll often just assume that our group is the additive group of integers because we can efficiently compute this mapping. And if you want to see more on this, there are a bunch of papers that have gone over what's called known order group actions. So let's define some hardness problems for group actions. So here I'll just put on the screen the group action discrete log, CDH and DDH problems. And I'll note that these are very analogous to the traditional definitions over groups. You really just replace, exponentiation with the group action operation, and the definitions are similar. Like for discrete log, for instance, given two set elements x1 and x2, the problem is just to find some group element such that g star x1 is equal to x2. I'm going to ignore some of the subtleties with sampling elements. So for now, we'll just assume that everything is uniformly sampled. Now, it turns out that you all have probably been using group actions for much longer than you've noticed. Group exponentiation is just a group action. And how is this the case? Well, if we set the set of our group action to be the group G, and we set the group to be the exponent space ZP, then group exponentiation is just a mapping that obeys the axioms of the group actions. And this is a little bit special and confusing because the set is a group, and this causes the quantum insecurity. And the main issue is that there's a set mapping for group exponentiation, which is just group multiplication. And in general, for group actions, there's no structure preserving set mapping. So it turns out that many other cryptographic group actions, assumptions are group actions in disguise. I'll talk about isogenies in just a second. Stickles key exchange protocol and related work, if you've ever seen that, as well as very recent work done on the semi-direct discrete logarithm problem are all group action based. So let's talk about isogenies. As I said before, certain isogeny-based crypto primitives can be modeled as group actions. I don't really want to go into the gory details of this because there have been a number of papers that are written specifically on this topic. But I'll say that psi-fish and its derivatives are effective group actions, as we defined earlier, and our work will directly apply to this. Seaside is a bit more complicated. Classically, it's something called a restricted effective group action. Our results apply here with some caveats, and I'll explain this more in a minute. And finally, SIDH and some recent follow-ups on that are not group actions. And luckily for us here, these recent attacks do not appear to apply to group action-based isogenies. So one last thing on group actions, sort of how do they work? Key exchange from group actions is very simple. So if we have an abelian regular group action where the CDH problem is hard, well, setup is quite simple. We just start with the group action and we pick an initial set element. And Alice and Bob run a symmetric protocol where they each sample a secret group element. They compute the action of the initial set element with their group element. They send that to the other party, and then they can generate a shared key using their own secret group element. Correctness holds by the properties of the group action, and the hardness just follows almost immediately from group action CDH. So you might be asking, why should we study group actions? Well, almost all of our post-quantum crypto systems are based on lattices. And what if an advance in lattice cryptanalysis, say, renders these schemes much more efficient because we have to use larger parameters? As NIST suggests in their updated call for post-quantum digital signatures, we don't want to put all of our post-quantum eggs in one basket. And it turns out abelian group action-based key exchange protocols, like those from isogenies, are some of the most promising alternatives. But these constructions are very new, and the security is not super well understood. And this has led to some surprising results, like the excellent work done on attacking SIDH recently. So what can we do? We're looking for ways that we can establish confidence in group actions. And that's sort of the point of our work. Our main result is that we show the group action CDH and discrete log problem are quantum polynomial time equivalent for abelian group actions. And this is nice because key exchange requires CDH hardness, but the security analysis is much easier, and the security problems generally are much easier to state for discrete logs. So this gives us sort of a best of both worlds thing. And we sort of solved this folklore problem stated by Benet and Lipton about the Diffie-Hellman protocol being equivalent to discrete log, although we obviously only solve it for the quantum case. and the much more famous and hard and interesting classical case is still wide open. So why does this matter? Well, you can probably guess what I'm going to say here, but it's good to have confidence in existing group action protocols and simplify what's sort of needed for these big attacks. And for theoretical security now, we only need to focus on the discrete log problem, not the CDH problem. This also makes building new group action-based key exchange protocols easier, because if you want to build a new group action-based key exchange, you really only need to focus on the hardness of the discrete log problem, not the more complicated CDH problem. And this has sort of already been used for some new constructions. And finally, I think it's just good to understand group actions since they're so ubiquitous in cryptography. So some other results we have. We show that generically group action DDH and CDH are not equivalent. We construct a very basic generic group action model that we use in some of our other results. We conjecture that the dihedral hidden subgroup problem is equivalent to discrete log on a generic group action. We show a very little bit of evidence suggesting this. And then we have a bunch of results on what's called restricted effective group actions. And these are sort of used to model Seaside classically. So informally speaking, a Riga is a group action where the action can only be computed on a fixed set of generators. And we define this problem that we call Riga cis here. And we show that if you can solve this problem, then our reduction goes through. But we also show a bunch of other connections between this problem and Rigas. Like if you can solve discrete log on Rigas, then you can solve this kind of lattice problem in disguise. So we have a bunch of results on this, but there's a lot of work left to be done to fully understand this connection. So with that in mind, let's go over some of the core techniques of our main reduction. The starting point of our work is an ePrint note from Galbraith, Panny, Smith, and Vercauteren that essentially encapsulates the following idea. Suppose we have an abelian group action and we define a CDH function relative to a base set element X that just does exactly what you think it does. It just outputs the CDH of two elements. Now, suppose we had a perfect adversary for this CDH problem. Well, the observation is that this adversary induces a group operation on the set X so that the tuple of X and the adversary forms an abelian group H. And this is not too difficult to verify. The elements of H are just the elements of X. The group operation is the adversary's computation. The identity element is the base set element. Inverses exist. You can see that the group would be abelian if the group action is abelian. And closure and associativity are also pretty straightforward. It's also the case that if G is ZP, then discrete log is well defined over H. You can sort of have a nice notion of exponentiation. I just put up a couple of examples why that might be visible there. And we can assume this, remember, since we can compute this mapping for any abelian group G if we have a quantum computer. So the core idea of GPSV18 is to consider this A-induced abelian group H and notice that a group action discrete log challenge on the abelian group action is just a regular discrete log challenge on this induced group H. And then we can just apply Shor's algorithm and solve for G. The problem for this is that we need a very low error rate on our CDH adversary A for Shor's algorithm to work. So it could be possible that group action CDH was broken with probability 0.9, which would effectively break key exchange, but the discrete log variant was still hard. And so this problem was left open for non-perfect adversaries. So the core approach of this work is to take a CDH adversary with non-negligible advantage and amplify it to essentially arbitrary advantage. And then we can follow the roadmap suggested by GPSV18 and complete the reduction. To show how this works, I'm going to start by explaining a method that doesn't work, and one that you're all probably familiar with, which is classic group-based CDH amplification. So you all have probably seen this in your introductory cryptography class. Many of you have probably taught this reduction. But suppose we consider an adversary that on input G to the A, G to the B, outputs the correct CDH tuple, which is G to the AB with probability P, and G to the UAB with probability 1 minus P for some element U. Now this is a simple adversary, and it's a pretty good adversary, but it'll be useful to examine So obviously, given a challenge instance, we can re-randomize it, right? We can sample random integers, we can multiply in random group elements. We can call the adversary on these randomized terms. Sorry, this is running over. We can cancel out the re-randomization terms, and then we get, these de-randomized terms. With probability p, we get the right answer, and with probability 1 minus p, we get something else. And the key point is, with probability p, we get something fixed, and with probability 1 minus p, we get something that's uniformly random in U. And so we can leverage our adversary into an almost perfect adversary through repetition, as only the correct answer is likely to be repeated in any polynomial number of trials. The problem is this doesn't work for group actions. We critically use the fact that we could multiply group elements, and there's no analogous operation for set elements. So if we try to go through this process for group actions, we have an adversary that does almost exactly the same thing as before, AB star X with probability P and UAB star X with probability 1 minus P. We could try a similar approach. We could re-randomize, call the adversary, de-randomize, and then get output. But the problem is we're getting the same output here, and we really don't gain anything from re-randomization. So what can we do with this? Well, in the previous example, sort of the obvious thing to do is to say, well, if P is not too close to 1/2, we can just sample enough times, right? And then we can apply some statistical bound. But what if P is equal to 1/2? What do we do? And here I'm going to introduce just a little bit of extra notation. I'm going to overload the CDH function, and I'm going to define an identity element. The first idea is the following. Suppose we run our adversary and get both AB star X and UAB star X. And if we run it enough times, presumably we'll get them both, right? We can get them both, but we don't know which one is right and which one is wrong. So what if we feed these back into A? So the key observation is the CDH function is sort of invariant over feeding it the identity, right? If I send you a CDH function in classical groups of like G and G to the B, it should respond G to the B, right? So we can apply this adversation and use it to sort of catch the adversary cheating. So in this case, right, if we feed these terms back into the adversary, A on X and AB star X will output AB star X and UAB star X, whereas A on X and UAB star X will output UAB star X and U squared AB star X. And note that the second set of outputs is different from the first one if U squared is the identity, whereas the first set of outputs is the same. And so if U squared is not equal to the identity, this allows us to tell which output is correct with probability 1. And we can naturally extend this idea to other distributions as well. So this sort of leads into a strategy we use in our proof that's called shift invariance. And for this slide, suppose G is a prime order cyclic and little g is a generator of this group. We can, I emphasize not efficiently, even quantumly, we can't efficiently compute this ordering, but we can order set elements such that the ith element is G of the I star X. And this gives us sort of a picture of shifting, where if we let A prime denote the distribution of A sort of run many times, you can either think of an empirical or imaginary distribution. Then we sort of put A prime of X on the top and A prime of WX on the bottom, where W is just G squared X. And you can see that this is just a shift. So as I said, we can't use this ordering without solving discrete log, but it's useful to think of shifts this way. And the point is, we can check for equality and matches across distributions. And sort of we can see that only distributions that shifts to themselves cannot be distinguished from correct. And this is sort of the core fact of our proof. But I left out one important case. So what if U squared is equal to the identity? So our approach from the previous slides will not work since the distributions will be equal. However, in this case, we can observe that the adversary essentially acts as a perfect CDH algorithm on the subgroup induced by G mod the elements generated by U. And we can just directly apply the approach from GPSV18 to this and then just brute force. And again, this idea can work for more general subgroups as long as they're polynomial size. And that's about it. We show that there's always a polynomially sized subgroup H such that we can amplify an adversary to have near perfect success probability on G mod H. You all can probably recreate the reduction from here. There are a couple of tricky parts. We could have super polynomially many possible subgroups if we're given a degenerate enough G. So we have to explicitly compute the subgroup rather than guess it. There are also some tricky points with respect to thresholdization, but this is really more tedious than interesting. I'll finally say that we assume a regular abelian group action in our reduction, but we can expand it to any abelian group action without too much pain. And if you're interested in that, it's all in the paper. That being said, there's a lot of room for improvement. So our reduction is almost black box, except the dependency on Q, which is the adversary's success probability. The running time is polynomial, but it's pretty bad. It's 1 over Q to the 13, where, you know, that's not great. So it's useful for ruling out quantum polynomial time attacks, but not necessarily for setting practical security parameters. For practical parameter setting, you know, you probably need 1 over polylog in the number of queries, and this might rule out our shifting technique, but maybe there's a better technique. And finally, in the same vein, it might be possible to do substantially better for fixed groups known in advance, particularly ones that don't have too many subgroups. A smart Asiacrypt reviewer pointed this out for SciFish. And it might be possible to have very tight instantiations for things like SciFish, and we leave this totally open. And finally, we think our work on Rigas and the dihedral hidden subgroup problem really just scratched the surface. So on that, thanks a lot for your time, and I'll be happy to answer any questions.
We have a couple of minutes for questions. Anybody? All right, then let's thank the speaker again. Our next talk is remote. So let's just take a minute to set that up. Can they hear us?
Hi, Shweta, can you hear me?
Yes, Shikhar?
Yeah, hi, can you hear me?
Yes, we can hear you. So our next talk is cryptographic primitives with hinting property. And this paper won the best paper by early career researchers. It's by Shikhar Patranabis and Naveed Alamati, and Shikhar will give the talk. Please go on.
Thanks, Shweta. Thanks a lot. And my apologies for not being able to give this talk in person. So welcome to this virtual presentation on cryptographic primitives with hinting property. This is joint work with Naveed. So we encounter hints frequently in daily life. For example, when we forget passwords and the hint allows us to guess the password without actually revealing the entire password itself. But it turns out that hints are actually also useful, not only in real life, but also in cryptography. And in the context of a widely used and fundamental cryptographic primitive called a pseudorandom generator that I believe we are all familiar with. Now, in the traditional PRG game, a distinguisher on an adversary is not given any additional information about the seed of the pseudorandom generator. But in Crypto 2019, Coppola and Waters introduced a variant of PRG, which is called a hinting PRG, and which is the fundamental motivation for this talk, where the distinguisher is actually given some additional information or hint about the seed of the PRG. More formally speaking, let's say that we have the output of the PRG as a sequence of n strings, each of length n bits, and we also have a sequence of n random strings of length n bits. And then we swap these two strings in certain positions, depending on whether a bit of the seed is 0 or 1. In particular, we swap them if the bit is 1, and we don't swap them if the bit is 0. So here's a toy example for n equals 6. So you can see that the y and z vectors are swapped in the locations where the seed s is 1. Now, informally speaking, what the hinting PRG guarantees is that despite embedding information about each bit of the seed in this 2x n matrix, this ensemble of strings actually remains pseudorandom, That is, it is computationally indistinguishable from a 2x n matrix of random n-bit strings. And more formally speaking, this is what the hinting PRG game looks like, where we have a 2x n matrix Z, and its elements are either the output of the PRG or uniformly random, and they are swapped depending upon whether each bit of the seed is 0 or 1. And despite encoding these additional hints about the seed, this matrix Z remains pseudorandom. Now, why are hinting PRGs interesting? In the seminal work, Coppola and Waters showed that it is actually a cryptographic booster. Well, we are all familiar with boosters in this era of COVID. But hinting PRG is a cryptographic booster in the sense that it can be used for a genetic transformation from CPA to CCA security for public key encryption and other advanced forms of encryption. And in more recent years, hinting PRGs have been used in a myriad of other cryptographic applications, in particular for new constructions of advanced cryptographic primitives. This makes hinting PRGs a very interesting class of primitives to study. Another interesting feature of hinting property is that it bears some similarities to another property that we are probably familiar with, which is circular security in the context of symmetric key encryption. In fact, one could view the hinting property as a deterministic form of circular security with respect to the bits of the PRG. However, there are some fundamental differences between the two. Historically, circular secure symmetric key encryption has been extensively studied, and we know how to realize them via simple constructions and proof techniques from certain standard decisional assumptions. And it is also known that they're weaker than public key encryption because they can be realized from random oracles and are hence black box separated from public key encryption. On the other hand, the known constructions and proof techniques for hinting PRGs are rather complicated and deeply rooted in algebraic or public key style mathematical assumptions, which naturally leads to the question of whether such kinds of public key techniques are inherent to hinting PRGs, or whether we can have simpler constructions and potentially non-algebraic constructions as well. So here's the one-slide summary of the current landscape of hinting PRGs and how we know to realize them in practice and what they imply versus what we ask in this paper. So to summarize, we ask three main questions. One, can we have simpler constructions and proofs of hinting PRGs? And can we realize these constructions from a wider class of assumptions, for example, isogeny-based assumptions that Hart gave us an excellent introduction? Then we ask whether we can extend the hinting property to other symmetric key primitives, and if such extensions are useful and realizable. And finally, we ask what exactly is the cryptographic complexity of hinting PRGs, and more concretely, can we establish whether mathematically structured public key style assumptions are truly necessary to realize these primitives? In this paper, we propose new extensions of the hinting property to another well-studied class of symmetric key functions called pseudorandom functions, and also their weak variants, where pseudorandomness is only guaranteed on uniformly sampled inputs. We also provide new security definitions for these primitives, where informally speaking, the pseudorandomness guarantee holds in the presence of hints about the secret key. But an important feature is that the security notion here is multi-evaluation, in the sense that the pseudorandomness guarantee holds over multiple evaluations of the PRF over different inputs. And this is in contrast to the security definition for hinting PRG, which is kind of one shot in the sense that you only get to see the evaluation on a single seed. So a hinting PRF implies a hinting weak PRF, which in turn implies a hinting PRG, all of these in a black box manner. Next, we show new stronger implications of the hinting property when extended to weak PRFs. In particular, we show that a hinting weak PRF implies a full-fledged circular secure symmetric key encryption scheme in a black box manner. This is in contrast to a hinting PRG, which only implies a weak notion or a one-time notion of circular secure symmetric key encryption. Next, we show, this is the major contribution of this paper, we show a new framework for designing hinting weak PRFs and by extension hinting PRGs. And our framework gives significantly simpler constructions and proofs as compared to the previous approaches like the missing blocks framework and the accumulation framework. And a corollary of this simple instantiation is that we can actually extend this to other assumptions, such as isogeny-based group actions, which we already heard about. Finally, we have an impossibility result where we show that hinting PRFs, and in particular this whole ensemble of cryptographic primitives with hinting property, is actually black box separated from public key encryption, And so public key style assumptions are actually not necessary to realize them. And we show this by showing a non-algebraic construction of a hinting PRF given just a simple random oracle. We also have some additional contributions wherein we show new strengthenings of the hinting property to what we call a functional hinting property, where the adversary is now given hints about each bit of some function of the seed, and this function can actually be chosen adversarially from a fixed function family. So here's an example. Suppose we have an n-bit seed for a hinting PRG, and a functional hinting property, for example, allows the adversary to get information not only about S, but also about each bit of this particular quadratic function of S, right? And we then show that the functional hinting property can have even stronger implications. In particular, we show that a functional hinting PRF with respect to some function family F implies in a black box manner a KDM secure symmetric key encryption scheme with respect to the same function family. Recall that in the normal hinting weak PRF case, we only got a black box construction of circular secure symmetric key encryption, and the amplification to KDM security was non-black box. However, the functional hinting property now gives us a new approach for achieving KDM secure symmetric key encryption in a black box manner with respect to Boolean function families. Finally, we also show that these kinds of functional hinting primitives can actually be realized from certain standard assumptions. In particular, we build upon our construction of hinting weak PRF and hinting PRGs from DDH to show a construction of functional hinting weak PRF and by extension functional hinting PRG with respect to function families containing projective quadratic functions and functions of higher degree over the bits of the secret key or the secret seed in case of the PRG. So this is kind of a one-slide summary of our contributions. So here's an outline for the rest of the talk. I'll spend the next few slides trying to outline how do we construct a simple hinting PRG from the DDH assumption. I will then give a brief overview of how we extend the same techniques to build a hinting PRG from cryptographic group actions. And I will give a very, very brief introduction to hinting weak PRFs. And finally, I will end with summary and some open questions and future directions of research. Right. So the simple hinting PRG from DDH is in fact incredibly simple. I think that many of you are probably familiar with this construction. It is a very, very simple construction that literally consists of a matrix vector multiplication in the exponent of the group element, where the matrix is a uniformly random matrix of square dimensions. And the vector is a binary vector. Okay, so remember that in the definition of hinting PRG, the seed is typically considered a sequence of bits, and we do the same. Now, it has been implicitly or explicitly proved in a number of previous works that if we assume that the group G is DDH hard, then this particular function is in fact a PRG. And the hint is that the proof of security requires applying the leftover hash length. Now, what we claim in this paper is that this PRG, this very, very simple PRG from DDH, in fact, already has the hinting property. And the way we prove that is that we reduce the hinting property of this PRG to its fundamental pseudo-randomness guarantees. So I'll try to briefly outline what our proof looks like. Our proof basically is a reduction that takes as input the public parameter M for this particular PRG, along with a sequence of n group elements, which is the output of this PRG, or it's a uniformly random sequence of group elements. And what this reduction outputs is a public parameter for the hinting PRG, which by the way is the same construction. So it basically outputs a different public parameter from the same distribution. And then it outputs this 2 cross n matrix, which if you recall is the output of the hinting PRG game. And this is either distributed as in the real hinting PRG game, which means that it is the intersparse of the real PRG output and a uniformly random sequence of group elements where the positioning is done based on the seed, or it's a uniformly random sequence. And the main challenge here is that our reduction actually does not have any idea about the seed of the original PRG, because it only gets this public parameter and the output, which is not supposed to reveal any information about the seed if the original PRG is secure. And despite that, what we want to do is that we want to ensure that when the input on the left is distributed as in a real PRG game, we want the output on the right to be distributed as in the real hinting PRG game, which means it needs to embed some information about the seed. And the crux of our proof is how we do this without knowing the seed in the first place. Okay. And of course, we also want random to map to random. And this is in a nutshell what a reduction looks like. It looks quite simple. So what we do is we basically output the same public parameter, except that we shift the matrix in the diagonal by some uniformly random shift elements. And then in the output sequence, we basically set everything on the top row to be directly equal to the input from the PRG game. And we shift the elements in the bottom row by these uniformly random shifts. Okay, so in other words, Zi0 is equal to Yi, and Zi1 is equal to Yi plus Di. Now, this is a simple looking transformation, but the interesting fact is that this implicitly allows us to embed information about the seed in the sequence on the right. Why? Well, let's see that. Suppose that the Yi's are actually distributed as in the real PRG game, and the Zi's are constructed as we said. It turns out that if the bit Si is 0, then it is easy to prove that Zi0 is actually distributed as it should be in the real hinting PRG game. This is because because when Si is 0, there is no contribution from the ith row of the matrix into Zi. And so since it only differs in the diagonal element for which the contribution is 0, so Zi0 is actually well distributed. On the other hand, Zi1 is randomly shifted, and so it is distributed uniformly random. Similarly, when Si is 1, we can argue that Zi1 is now actually distributed as the inner product of the ith row of the matrix and the seed, and Zi0 is distributed uniformly random. Okay. So in some sense, we embed information about the seed into these elements without knowing the seed at all in the first place. And of course, it's we achieve this goal that when the Yi's are distributed as in the real PRG game, the Zi's are distributed as in the real hinting PRG game. And of course, it's easy to see that when the Yi's are distributed uniformly randomly, then so are the Zi's. And so, when the input is random, the output is also random. And so that essentially concludes the proof of the fact that this PRG is in fact a hinting PRG. And this construction is much more simple and direct as opposed to the existing approaches for constructing hinting PRGs. So now I'll very briefly discuss the fact that our simple approach for constructing hinting PRGs readily generalizes to cryptographic group actions, which are commutative and regular. And I think Hart already did an excellent job of introducing group actions, so I won't go into the details, except maybe again recall that group actions are useful because they can be instantiated in plausibly post-quantum secure manner from certain families of isogens. And I'll just throw the construction out there. I won't go into the details, but again, what I would like to sort of stress is the fact that our simple approach allows us to get very simple and direct constructions of hinting PRGs from group actions. And this is essentially a generalization of the construction from plain DDH that we can prove secure under a special assumption called the linear hidden shift assumption that we introduced way back in 2020 in our Asiacrypt paper. I won't have time to go into the details, so I would refer to the paper for more details on the construction and proof. And finally, I would like to provide a very brief overview of hinting weak PRF. So, as I already mentioned earlier, that when we extend the hinting property from PRGs to PRFs, one thing we need to ensure is a multi-evaluation kind of definition, where we now have the key of the PRF, which is an n-bit string, but we also can have a sequence of any polynomially many inputs, which can be either arbitrarily sampled or uniformly sampled for a hinting weak PRF. And then what we do is we basically apply this swap to each of these output sequences. And so in some sense, what we have here is a multi-evaluation hinting property, where each evaluation leaks some information about the secret key. And yet this whole ensemble of outputs across multiple evaluations remains computationally indistinguishable from uniformly random. So this is an informal overview, and I would refer to the paper for the formal definition. And then this is kind of a one-slide summary of the fact that we can actually take our simple approaches for constructing hinting PRGs from DDH and from group actions, and we can very naturally extend them to construct hinting weak PRFs from the same assumptions. In particular, if you look at the left, you can see that our hinting weak PRF from DDH is nothing but the same hinting PRG construction, where the secret key is now acting like the seed, and the public parameter essentially becomes the input. And our proof techniques are also very, very similar. Nonetheless, this is a very kind of high-level overview, and I would refer to the paper for the more detailed constructions and proofs. Right, so now I would like to conclude by summarizing our results and stating some open questions. So we showed how to construct hinting weak PRFs and hinting PRGs, as well as functional hinting weak PRFs and functional hinting PRGs from certain standard assumptions. But we do not have any constructions of hinting PRF or its extension to functional hinting PRF from standard mathematical assumptions. So this is one open question. The other open question is whether we can realize primitives with the functional hinting property from a wider set of quantum safe assumptions such as lattices or isogenies. In particular, our current constructions are kind of specific to DDH, and we believe that some more work will be required in order to be able to build these from lattices or isogeny-based assumptions. And finally, we leave it open to investigate additional applications of these new primitives with hinting property and functional hinting property that we introduce in this paper. Of course, I didn't get time to go into the details of certain results, such as the black box separation result, as well as the results on the functional hinting property. And I would again refer to the paper for more details. Thank you, and I'll be happy to take any questions.
We have time for questions. All right, then let's thank the speaker again. Thank you.
Thank you. Thanks, Ratan.
All right, so let's move to the last talk of this session. This is a work on SwiftTC by Jorge, Francisco, and Mehdi. And Jorge will give the talk. This is the paper that won the runner-up best paper award and was invited to the Journal of Cryptology.
Okay, good morning, everyone. So I will be talking, can we go full screen? Oh. That's weird. Okay. So I'm going to be talking about SwiftTC, which is the Shalhoub and the Bush-Stein indifferentiable function to elliptic curves. So the contribution of this work is the most efficient constant time admissible encoding that works for a large set of ordinary elliptic curves. So what does this mean? Well, in particular, it's a big leap for hashing into these curves because it results in the first constant time admissible, indifferentiable hash function that requires a single square root computation, as well as an efficient point representation algorithm, which requires only 2 square root computations. So just as a background, a lot of applications in cryptography are going to require us to hash into a cryptographic group of interest. And if this is something like a finite field, then it can be just as easy as hashing into a long bit string and interpreting this mod Q. But when I'm working with elliptic curves, this can be not trivial at all. So basically, the question that we're trying to tackle is how can we get x and y coordinates that are random among the set of points that satisfy this specific curve equation. So let's first take a look at some naive constructions that don't quite make the cut. So the first one and most obvious that I can think of is I can just hash into an x coordinate. So this is a field element, so I know how to do it. And then I just have to ask whether or not this is the x-coordinate of a point in the curve. So the elliptic curve is given by y squared equals some function of x. So I can just evaluate this function of x and try to take the square root, right? So if it exists, then I found a point in the elliptic curve and I am done. But if it does not exist, I have to start over and try with a new x. So I have to implement some kind of try and increment approach. And obviously the problem with this is it's not going to be constant time. And we're going to be open to timing attacks. So just the knowledge of how many times I had to restart can give away valuable information about what was the seed. So we don't like this. Another construction we can think of is you may know that points in the elliptic curves form a group. So I can pick a generator of this group and hash into a random multiple of this generator. So I hash into an integer n, and then I compute the point p equals n times the generator. So this looks like a very good idea, but it's actually a very bad idea because it leaks very sensitive information. So whoever computed this hash function not only knows the value of the output p, but in the process, he also learned the value of n. So this is what we call the discrete logarithm. And it's in most applications, it's precisely what we want to keep secret. And we assume that it is hard to compute. So you can easily see how, depending on the application, if we're not careful, this can end up compromising security very, very badly. So we would like to get something that works regardless of the application. And in general, the strategies that tend to work better are based on some kind of modularity. So I assume that I already have a hash function into some set S. It can be something like a finite field or anything different. And then I compose this with something that I call an encoding. So the encoding is just going to be a function from my set of interest, in this case, to the elliptic curve. And I'm going to assume also that I have an inverse function that takes me from the curve back to the set S. Usually we call this the point representation function. And if you're familiar with the alligator construction, for example, this is precisely the idea that it's based on. So in our case, we're going to present algorithms for both of this. We have the encoding function that we call SwiftC, as well as the point representation function, which we call alligator Swift. All right, so what do we need for this construction to be secure? Basically, if we already have our hash function into S and compose that with the encoding, when is this composition sure to be a secure hash function itself? It turns out that it is enough for the encoding to satisfy three properties. It has to be efficiently computable, of course. It also has to be regular, meaning that for uniformly random inputs, the distribution of images has to be also statistically close to uniform. And also it has to be sampleable, meaning that I need to have this inverse function that computes per images. And usually the encoding is not a one-to-one function, so there can be more than one per image. So in that case, we just ask that it returns any of the possible per images, but it has to do so uniformly at random. It cannot have any bias for a certain per image. So if the encoding satisfies these three properties, we say that it is an admissible encoding. And it turns out this is enough to allow us to just use it as a black box and not have to worry about compromising security. So let's first look at a very simple example, which is an encoding not to an elliptic curve, but to a conic. So I have plotted here a conic over the real numbers. And conics have this very interesting property that any line that intersects it is going to do so at exactly 2 points. So I can exploit this to build an encoding. What I do is just fix a reference point, P0. And then for any other point in the conic, I can just draw the line connecting P0 to P1 and compute the slope of this line. So for the point P1, it is going to be associated with the slope T1 of this line. And I can do this for any other point in the conic. So this is actually an encoding from slopes, which are real numbers, 2 points in this conic. It turns out this is, in fact, an admissible encoding. And even better than that, it is a one-to-one function. So it's going to be very well behaved. However, keep in mind that this works only as long as I have pre-computed or somehow know a fixed reference point in this conic. So just keep this in mind because it will be important later on. All right, so now let's move on to encodings to elliptic curves, which turn out to be a little bit more complicated. And the main ingredient that we're going to use is called the Shaloub-Van de Woestijn map. This is actually a family of encodings. So for each choice of the parameter u, which is a field element, I'm going to get a different encoding. And the way it works is that Shaloub and Van de Woestijn find a map that goes from a certain conic to a certain hypersurface. So this certain conic is given by this equation, and it's a parameterized conic because the coefficients are given by these polynomials of the parameter u. And this hypersurface is just this hypersurface in a 4-dimensional space given by c squared equals g of x1 times g of x2 times g of x3, where g of x is just the polynomial of the elliptic curve. So these are the explicit equations for the map. You don't need to worry too much about them. Just know that there is a map from here to here. And at this point, you might be wondering, okay, but this is not an elliptic curve, and this is not an elliptic curve. So why am I talking about this? Well, it turns out that from here, we're very close to getting to a point in an elliptic curve. So if you look at the equation for B, I have a square, which is equal to the product of 3 things. So when this happens, it must be the case that at least one of those 3 things is a square. And in fact, there's only 2 possibilities. It can be that exactly one of them is a square, or all 3 of them are squares. And remember, if I find an x such that g of x is a square, then I have actually found a point in the elliptic curve. So all that we have to do after we get our values for x1, x2, x3 is do a quadratic reciprocity test to determine which one of these is a square and return that value. And in the case that all 3 are squares, we just have to do any arbitrary choice. So let's say, for example, that I prioritize x3. And by the way, the quadratic reciprocity tests are much cheaper than a real square root computation, at least by an order of magnitude. So in the end, we only ever have to compute a single square root for the value that is in fact a square. And this is actually going to be the main cost of the algorithm, a single square root. Now, on the other hand, we already know, we talked about how to encode into this conic. So we can actually build the whole chain that is known as the Shaloub-Van de Woosten map. We start with a field element, which is the slope of the line. We use the encoding that we talked about first to get a point in the conic CU. Then we apply the map that I just mentioned to get a point in B. And then we do the quadratic reciprocity tests to figure out which one of those is a point in the elliptic curve. So this whole path is what we know as the Shaloub-Van de Woosten encoding. And these are given by very simple formulas, explicit formulas, so it's easy to implement in constant time. And the main cost, as I said, is a square root computation, and this is just to recover the y-coordinate, right? So if I don't care about the y-coordinate, which is the case in some applications, I can actually skip that. And this works basically for all elliptic curves and almost any choice of the parameter u. However, the disadvantage of this, as beautiful as this all is that for any choice of u, the encoding fu is actually not regular. So this is not an admissible function, and I cannot use it as a hash. So that's too unfortunate, but there is a solution that we call the squared encoding construction. So the way it works is, okay, one evaluation of fu is not regular, but it turns out that if I take 2 independent evaluations and add them together, then the result actually is regular, okay? So now I'm gonna have a domain size that is twice as large, but I'm actually going to get an admissible encoding, and it's an admissible encoding that works for basically all elliptic curves. However, the disadvantage of this is that now I have to compute 2 copies of f, therefore 2 square root computations, so it's gonna be a little bit more expensive, but this was the best previously known way of doing this. So this is where our new proposal comes into play, what we call SwiftC. And what we're doing is we're still using a domain size that is twice as large, but now the second variable is going to be u itself. So before it used to act as a global fixed parameter, but now it's actually going to be another input. So we're computing a capital F of u and t, which is equal to lowercase fu of t. Okay, so if I tell you that this is the whole idea of the construction, maybe it sounds a little bit underwhelming, like we're just changing the notation. But of course, this has very deep implications. So there are theoretical implications because, of course, it sounds reasonable that if I randomize u as well as t, probably I'm going to get more random looking points. But to get a formal proof of regularity is a whole different thing. And there's also practical implications because now I need an algorithm that will be able to evaluate fu of t for any choice of u that will be determined at runtime. Okay. However, over the whole FQ square domain, this construction will show that it is in fact admissible. And what we gain is that we're back to having to compute a single copy of f, therefore a single square root computation. So this should be and is in fact roughly twice as fast as the previous state of the art. Okay, so let's first talk about these practical implications of building this algorithm. And the place where you're going to run into trouble is for the encoding to the conic. So if you remember near the beginning of the talk, I mentioned for this to work, you have to know a reference point in the conic. It can be any point, but you have to have some way of finding at least one point. So this is what I had called P0 before. Now I'm calling it PU because it is the conic itself is a function of the parameter U. So I need an algorithm that given the conic CU will return some reference point PU. And it turns out that this is a problem that had already been studied by Van Hoysch and Cremona. And they showed the following theorem. So if I have this conic that is parameterized by these polynomial coefficients, H of U and G of U, it turns out that there is an efficiently computable point in this conic given by rational equations if and only if two conditions are satisfied. So minus H has to be a square mod F, mod H, sorry. Minus G has to be a square mod H, and minus H has to be a square mod G. So as long as these two conditions are satisfied, their proof is constructive, so I can use their algorithm to output a point PU, and then I just carry on with the rest of the construction exactly as before. Now, in our case, the polynomials H and G are not general, but they have this very specific form. So H is equal to 3U squared plus 4A, and minus G is just the polynomial of the elliptic curve. So in this particular case, we show in the paper that the conditions that I just mentioned are actually equivalent to another set of three conditions, namely that the size of the field has to be equal to 1 mod 3. The discriminant of the curve has to be a square. And the third condition is that at least one of these constants, nu plus or nu minus, has to be a square. So if you look carefully here, condition 1 implies that minus 3 is a square. Condition 2 implies that delta is a square. So this whole thing is always a square. And if I take the square root for at least one of the choices of sign, I should get a quantity that is a square. So that is condition 3. So it's not at all obvious that these conditions are equivalent to the ones that I mentioned before, but it's a much nicer characterization of the curves that are compatible with our construction. So notable curves that are compatible include the NIST P256 curve, as well as 256K1, which is the one used for Bitcoin. And also all the BN and BLS curves, which are used for pairings, those are all immediately compatible as long as Q is equal to 1 mod 3. And then there's a few other curves which are not compatible, but that we managed to rescue using isogenies. So an isogeny is just a rational map that takes me from points in one curve to points in another curve. And so it may be in some cases that the curve itself is not compatible, but I managed to find an isogenous curve that is compatible. So I can just apply the Swift-DC construction to that other curve and then compose with the isogeny to get back to the curve that I wanted. So this is the case, for instance, for curve 25519. It is not compatible because the discriminant is not a square, but we found a curve that is compatible and is related by an isogeny of degree 2, which is very, very cheap to evaluate. So it has a very negligible overhead. And the same is the case for NIST P521. It is not compatible, but we also managed to rescue it, this time through an isogeny of degree 3. And then unfortunately, there's another case when Q is not equal to 1 mod 3. Here, isogenies don't really help us. And so far, we have no good way, no way at all of rescuing these curves. And unfortunately, this does happen for some popular curves, including NIST P384 and the Goldilocks curve. So those are not compatible. Okay, so that covers the computability of Swift-DC. Now let's talk about the second property, which was regularity. And let me be a little bit more specific about what we want to show. So if I have a function that is perfectly random, and I want to compute the number of preimages, on average, this should just be equal to the size of the domain divided by the size of the codomain. So in our case, the size of the domain is Q squared because we have two field elements, U and T. And the size of the codomain is just the order of the curve, in this case divided by 2 because we only care about the x coordinate and not the y coordinate. So there's a popular theorem called Hass's theorem that tells you that the order of the curve is roughly Q. So if you plug this in, you'll find that the number of preimages should be roughly equal to 2Q. So this is the main theoretical contribution in the paper. We show this theorem that if you take this error term, which should be equal to 0 if you plug this in, we show that, of course, it's not exactly 0, but the sum in absolute value is bounded by this epsilon, which is a function that vanishes exponentially fast with the bit size of Q. So asymptotically, the distribution of Swift-DC is going to be very close to a uniform function. And finally, let's talk about the samplability. So remember, this is being able to compute pre-images. And what we do is explicitly propose this new algorithm called alligator Swift, which given the x coordinate of a point will return a pre-image UNT. And the way it works is basically just you fix a randomly chosen value of u and try to invert fu of t. So when you're trying to invert it, you should ask yourself from what point in the conic could I have come from? And basically there's 3 different branches. So these are the equations for the map that I had mentioned near the beginning of the talk. So there's 3 choices. Either the square came from x1, in which case I have to invert the first map, or the square came from x2, in which case I have to invert the second map, or it came from x3, in which case I have to invert the third map. So I pick a random value of u, and then I pick one of these 3 cases at random, and I try to invert that corresponding map. So if this works, then I'm done, and I have a pre-image. But if it doesn't work, then I just start over. So I pick a new u, I pick another one of these cases at random, I try again. So basically, we're doing some rejection sampling to ensure that the distribution is going to be uniform. And it turns out you can actually reject failed samples by just doing quadratic reciprocity tests before committing to real square root computations. So in the end, you only have to compute square roots for the one successful case. And this is a big improvement over the squared encoding variant, where each failed attempt has the cost of another square root. And then, of course, once you get your point in the conic, remember the encoding to the conic was a one-to-one function, so that is very easy to invert. You can compute t from there, which remember was just the slope of the line. So the output is going to be the u that you picked at random and the t that you computed. Okay, so we have just a proof of concept implementation in Sage that is freely available. And what we do is count the number of operations that it takes. So we have the number of additions, squarings, multiplications, Jacobi symbols, which are the quadratic reciprocity tests, as well as inverses and square roots. And as promised, the main feature is that you only have to compute 1 square root, along with 1 inverse, which, by the way, can be computed in batch. And then, of course, if you only care about x-only projective coordinates, then you don't have to do either of them at all. And this is just a little test that we run with our implementation. So this is counting the number of pre-images of every point in the elliptic curve. So each of these bins represents a different point. And we just exhaustively evaluated SwiftDC for every single input. Obviously, this had to be done with a very small prime. So this is only a 10-bit prime, but already for this small size, you can see that the distribution is looking very close to uniform. It's a very good result. Okay, so just to conclude, SwiftDC is now the most efficient known way for indifferentiable hashing in constant time to a large set of ordinary elliptic curves. And alligator Swift is the most efficient point representation algorithm for the same set of curves. And some future work that we still want to do for this project is doing an efficient constant time C implementation for reference, as well as theoretical work to further increase the number of curves that are compatible. So with that, I would like to thank you very much for your attention.
Are there any questions? All right, so let's thank the speaker again. We'll now have the coffee break.
Let me announce again that the sponsor area is on the 4th floor, and there is quite a bit of food